So let me kick off by giving you a bird's eye view of the chip's architecture. Our chip consists of two tiles, and you can think of a tile as something similar to a traditional processor core. Each tile, you can see one here on the right and one on the left, has 512 kilobytes of RAM, and it has an arithmetic and logical unit, including a floating point unit and a vector unit that I'm going to talk a little bit more later on. What makes it special, and this is actually our own architecture at XMOS, is that each tile has what we call 8 logical cores. And you can think of a logical core as essentially a hardware implementation of a thread. So each logical core has its own register files, scalar as well as vector registers, but they share the ALU. Now these cores can execute simultaneously, and we give you hard real-time guarantees. So this is actually a very good choice if you have an application that requires hard real-time guarantees such as audio. Now this architecture gives you a couple of advantages. First of all, these cores can be programmed to do pretty much anything you want. And in particular, one thing you can do with them, you can use them to implement hardware interfaces in software. And that's in fact what we do. And this is the first design choice that allows us to keep the cost low, since we don't have to design or license hardware IP. The second thing is you have a lot of flexibility here, and you can use this essentially as a small SoC. You can run an instance of FreeRTOS, which we have recently ported to our platform, but you can also run a far-field microphone array. You can interface with a camera, and most importantly, for the context of this talk, you can run neural network inference on it. So before I go on to the demo, I'd like to give you a little overview of what infrastructure we use to deploy neural networks, and we have decided to go with TensorFlow Lite for microcontrollers, of which you, if you follow this webinar series, have heard before. Basically, the workflow would start with either you train your own floating point neural network in TensorFlow or some other framework, or you download one of the pre-trained ones. And as long as you can convert it to TensorFlow format and you can push it through the TensorFlow Lite converter and quantizer, our workflow will work for you. So once you have quantized and converted your model using the built-in quantizer converter, we provide you with a standalone tool that performs the platform-specific transformations and optimizations on your model. Now, this tool directly operates on the TF Lite models, and it outputs another TF Lite model with some custom operators in it that you can then deploy in our port of the TF Lite micro runtime. With that, we also provide a kernel library, which is, by the way, a standalone product. So if you ever decide that you want to write your own runtime or something like that, you can do that. And what I've decided to do here is just give you a kind of idea of how that workflow that I showed you looks like in practice. And I'm not going to go into detail very much on what's happening under the hood. What I really want to do is just show you what would be the steps if you were a customer of ours and you'd want to deploy on this device. So I picked a variant of MobileNet, and as you can see here, it's with alpha equals 0.25. And the only thing I'm gonna do to this is I'm going to restrict the number of classes to 10. Obviously, in your application, you would probably want to retrain, or probably you bring your own architecture. But for the purposes of this demo, this will work. And as you can see, it's just the kind of off-the-shelf MobileNet with a dense layer that outputs 10 predictions instead of 1,000. And what I want to highlight here is this model has 220,000 weights. So what we can expect after quantizing it to signed 8-bit integers is that the model size should be around 220 kilobytes plus some overhead. I prepared some example data so that we can do the quantization, and there are really no surprises here, just 10 examples of each of the first 10 classes. And before I move on, I'm just going to run inference on these using the floating point model in Keras, just so that we see what this model outputs for these 3 example images. And the next step in your deployment process would be to quantize this. Of course, if you want to do it, you can do quantization aware training and kind of skip directly to the quantized network. But this would be a typical workflow. So if you want to quantize a pre-trained floating point network, we give you essentially helper functions that wrap around the built-in quantizer converter. And it's really just so that you don't have to worry about the exact settings of the quantization that are required for xcore AI. So really it's just a couple lines of Python, and what it will give you is a quantized model that you can then, using the built-in interpreter, evaluate. And what you can see here is that for the goldfish and the ostrich, you have a little lower prediction probabilities, and then for the hammerhead, it's actually quite a bit off. And you could mitigate this effect, as I said, either by quantization-aware training or just training it properly on the classes that you actually want to classify on. Now, so far there isn't really anything platform specific. The next step would be to optimize this for xcore AI. So once you have that, and perhaps you're happy with your quantized model, we give you a converter, it's just a simple function that you pass in your quantized model, and out comes a xcore optimized quantized model. And to be able to evaluate this without having to actually run it on the device, what we decided to do is to implement Python bindings for an interpreter that essentially runs a TensorFlow Lite for microcontrollers runtime on your host with reference implementations of our kernels. This means that you can get bit perfect outputs in terms of what would be the output of the actual device. And what you can see here is we have results for the goldfish and the ostrich, which are indeed bit perfect to what the quantizer would give you straight away. And then with the hammerhead, we have a slight deviation from what the quantizer gives you. And this can happen. Our hardware implements different saturation and rounding rules than what the reference operators would do. But typically the result is very, very close. So with that, I am going to show you how our device works right now. And basically what we've done here is we've taken this MobileNet model and we've wrapped it in an application. And in your particular application, you would put other things in there, obviously. For example, you would run FreeRTOS, a Wi-Fi stack, other interfaces, and so on. But right now, I just started this, this program on the device, and it's listening and it's waiting for me to send some images there. And all of this is happening through a debugger right now. So the first image takes a little bit of time. There are some handshakes that happen there. But once it's sent to the device, you can see that some numbers come back. Let me start in the end, that indeed the prediction is bit perfect to what we've seen. It was 46.48% for the hammerhead. And then we also have some timings, and just to prove that this isn't something I set up earlier, I can run the same thing on the goldfish, and we should have same results. The timing should be the same. Again, we have a hard real-time guarantee here. And one of the previous questions asked about timing. Here, the total time is 18 milliseconds. However, about 8 milliseconds of this is due to the printing that's happening here. In practice, this model would run on around 10 milliseconds.